Hola. I would like to tell you a story. It's a true story about the triumph of goodness over badness. So we're going to start with this guy. This is Edsger Dijkstra, the first Dutch computer programmer. In 1972, the ACM awarded him the Turing Award in honor of some of the really important contributions he had made to computer science, including programming languages. He was on the Algol 60 committee, operating systems, concurrency, garbage collection. He did a lot of really important fundamental stuff. And when you win the Turing Award, you're invited to give a lecture. So this is a picture of him in San Francisco at the Palace Hotel, where he gave a lecture called The Humble Programmer. And it was a brilliant speech. And you can still hear it on YouTube today. It's worth listening to. His speech was full of a lot of really radical statements, things which were considered controversial or even offensive at the time, which turned out to be true. So when you listen to his talk today, it's hard to understand why people might have gotten upset. It's really a great thing, I think, to be able to go out in public and say things which make people angry, which turn out to be truth. I think those are the most important truths. They're the hardest ones to say. It's easy to get up and say things that everybody agrees with, but saying the thing that people disagree with, which is true, that's a much more important thing. Anyway, he is most remembered not for that speech, even though it was a really good one, but for having written a letter. In 1968, he wrote a letter to the editor of the communications of the ACM, and the editor accepted the letter and published it with the title, Go-To Statement Considered Harmful. That letter started an argument, a violent, disagreeable argument that went on for over a generation. So it's a really important letter, so I'd like to read it to you. For a number of years, I've been familiar with the observation that the quality of programmers is a decreasing function of the density of go-to statements in the programs they produce. What he was saying was an interesting thing, but he said it in maybe the rudest way possible. What he's saying was not that programs with go-to in them are inferior, but that the people who write those programs are inferior. That's really rude. That's arrogant. But he goes on. More recently, I discovered why the use of the go-to statement has such disastrous effects. Now he's demonstrating that he is a drama queen. He could have said, not as good, but he said disastrous. And I became convinced that the go-to statement should be abolished from all higher level programming languages. And this is what started the fight. He wasn't just saying you shouldn't use them or you should try to avoid them where you can. He was saying they should not even be in the languages, which was a very radical statement. And again, it started a fight. So let's look at the positions that people took as a response of that. There were the radicals, including Dijkstra, who said the go-to is a disaster, it must be completely eliminated. And go-to at that time was a really popular feature. Every important programming language, including Lisp, had go-to in it. So there were the reactionaries who said, no, we shouldn't do that, we should keep it. It's important, and they had lots of reasons. The first one was performance, that the go-to statement is obviously faster than the structured statements that would replace it, and we need that speed. Now, it turns out performance-oriented arguments are almost always wrong, as they were in this case, but we get really excited about the argument for performance. They argued for tradition, that we have always had go-to, it's part of who we are. My grandfather used go-to. Freedom. I need the freedom to express myself. I am an artist and I express my art with go-to statements. There was the pride thing. So obviously, inferior people can write inferior programs using go-to, but it is an insult to assume that I am one of those people. How dare you? You know, this is about me, isn't it? It's not about go-tos? No. And then there was the majority, that more of us think that we should keep using go-to than there are radicals who say we should get rid of it. There was also a meta-argument. We have more things on our list, therefore we must be right. Then in the middle were the moderates who were trying to make peace with both sides. And the moderates said, obviously there are problems with the go-to, we should avoid it where we can, but there are cases where it's an appropriate thing to do and we should use go-to in those cases. And this argument went on for over 20 years. And it was a loud, noisy argument, and none of the sides shifted from their positions. So let's look at the chronology of this. So we start in 1968 when Dijkstra starts his letter. Now, Dijkstra is not the first person to observe a problem with the go-to. Someone suggested to him in 1959 that maybe Algol shouldn't have the go-to in it, which at the time made no sense to Dijkstra. But living with that thought running around in his head for 9 years, eventually he learned the wisdom of it and decided, yeah, I guess we should get rid of it. The C language was designed by Dennis Ritchie. Dennis Ritchie was a moderate. He put go-to into the C language, didn't recommend that you use it, but it was there. And maybe he used it a few times. C++ comes a decade later, and it still has a go-to in it. A decade after that, Java comes out. Java does not have go-to. And the world didn't end. The reactionaries were saying, if you take away go-to, terrible things are going to happen. And nothing happened. In fact, what happened was programs became easier to make. Because what go-to did was it allowed us to write programs of greater complexity without that complexity becoming overwhelming. Who benefits from that? Well, we do. So the people who were arguing against the go-to were the people who would have most benefited from it if they could have understood how to adopt it. Now, it turns out the author of Java wasn't all that brave. He made go-to a reserved word in Java just in case there was a riot, and he could just turn it on and go-to would be back on. But they didn't have to do that. So progress does not wait for the next idea. It waits for consensus on an old idea. We think that we just wait for someone to invent something and we go, we've been waiting for that, and then we all move forward together. And that's not the way it happens. It's never happened that way. What happens is we have to wait for a generation to retire or die before we can get critical mass on the previous good idea and move forward. So the biggest problem we have in programming, obviously, is the bugs, right? Anyone ever made a bug? And imagine, yeah, a few hands went up. The honest hands went up. Bugs are a problem, right? And bugs came with the invention of digital computers. Maurice Wilkes was an Englishman who wrote one of the first von Neumann, or created one of the first von Neumann machines, and started programming it and came up with this terrible realization. As soon as we started programming, we found out to our surprise that it wasn't as easy to get programs right as we had thought. Debugging had to be discovered. I can remember the exact instant when I realized that a large part of my life from then on was going to be spent in finding mistakes in my own programs. Can you imagine how awful that moment was? We're still living it, right? We've made no progress on getting rid of bugs. So this was eventually observed and given the formal name, the software crisis. As computers became larger and the sorts of things we did became more sophisticated, a dark side appeared, that it was very common for projects to go over budget, to go over time, to produce programs that were unreliable, where the requirements weren't fully met, where the software was maintainable, and sometimes total failure, where the project never gets completed. And this still goes on, right? This was called the software crisis, and there was a lot of attention on it and a lot of meetings and effort to try to figure out a solution, and ultimately we just forgot about it because it never went away. We just stopped talking about it. So this still happens, right? Still happens way too often. So the mathematicians thought, well, there must be a formal mathematical solution to this. I mean, the mathematicians created the first generation of computers, and they thought they should be able to solve this problem. And being mathematicians, they thought the way we should prove it is with proofs. So that you write a program and you then write a proof which proves that the program will do what it's supposed to do. That tests can only prove the existence of bugs, not their absence, so testing does not fundamentally work. We need something better. And they thought it was going to be in mathematical proofs of programs. Unfortunately, it didn't work for a couple of reasons. One is that the proofs ended up being much more complex than the programs they were proving. And so that became unwieldy. But even more than that, often the thing that goes wrong in a program is that the specification is wrong. The thing that we were told to make is incorrect, and we only discover that in the process of making it. And there's no way a mathematical system can deal with that. So that was a big disappointment. Donald Knuth published a program that contained a comment which kind of summed all of this up. Beware of bugs in the above code. I only proved it correct, not tried it. So what to do? Well, another mathematician who was doing software thought maybe types would be the solution. The idea of types starts in the first high-level programming languages, where you've got a word which contains some number of bits, and depending on the context, those bits could represent a number, or a character, or a number of characters, or a floating point number, or an address, or an instruction. How does the computer know what's in those bits and how to interpret it? So the first high-level programming languages had type identifiers. You could say this is an integer, or this is real, or this is a character, or this is an address. And that enabled the software to know what sort of instructions to generate for each of those types. So the idea was maybe there's information in those types which we can apply to the correctness problem. One of the big advocates of this was Robin Milner, who created a brilliant language called ML. And in talking about his type system, he said, well-typed programs cannot go wrong, which we know is absolutely not true, right? Because they still go wrong. We've got types all over the place. And so there's sort of an argument going on now about type systems. There are the radicals who are saying types might be good someday, but they're not worth their weight. Types actually cause more problems than they solve. And then there are the reactionaries who are trying to maintain the status quo. You know, type is in most of our languages, and they want to keep it there. So they argue that type systems require, on your part, only a little bit of extra effort, and they're helping you. So don't resist, submit, and do what you're supposed to do. And there are the moderates who are trying to find peace in the middle, saying, well, you should use types where you think they help you, and you shouldn't have to use them where you don't have to. Ultimately, what's the right answer here? We don't know. We're still playing this one out. So I'm hoping that Milner's promise someday comes true, that someone figures out how to build a static type system which is not overwhelmingly complex, which is actually worth the freight, that will provide more benefit than cost. But I don't think we're there yet. So during the argument about the go-to, there was a joke about the come-from. You know, if we're going to get rid of the go-to, maybe we should get rid of the come-from. And what would the come-from statement be, and how would it work? And there were a number of funny articles written in journals about the come-from statement. Except it turns out it's not a joke. We have a come-from statement in all of our modern languages, and it's spelled extends. This is one of the things we see very often in classical programming, which is actually a terrible thing because it causes very tight coupling between classes, and that coupling is the source of terrible problems. So in ES6, which was published last year and which is starting to become available everywhere now, the best feature in ES6 is proper tail calls. A proper tail call happens when the last thing a function does is return the result of calling a function. It could be a different function or it could be calling itself recursively. And the compiler is required to not generate a call return as it would ordinarily, but instead to generate a jump. So a tail call is a go-to statement that takes parameters. And that is a brilliant thing. It's much better than the original go-to statement because it's much better structured, but it provides for much better performance. So the efficiency thing works in our favor here. And it allows for new kinds of programming, like continuation passing style. So this is going to be my most favorite feature of ES6 if it ever gets out. So you all heard of SSL? That's that crappy encryption link thing that was developed at Netscape that is still being debugged after 20 years. One of the most famous bugs was discovered a couple of years ago in Apple's implementation. It was called the Goto Fail Bug. And it was terrible. And this is the actual code. This is the code that Apple used. And this was a bug that broke security all over the internet. Really, really bad. And it's really, really simple. So looking at this code, there are a number of things which are bad about it. And it's not uncommon when you've got some code which contains a really serious bug, it contains a lot of other problems as well. So we've got things like they're doing an assignment in condition position in an if statement. You shouldn't do that. They left out the curly braces on the consequence of the if. You shouldn't do that either. That's what caused this to fail. Fail, it was the name of the, ironically, the name of the label to which control should go if the thing failed, but it was itself distracting because there were paths that got to that which were not passing back the failure code, which was partly why they missed it. And the big problem was that maybe there's a copy and paste error that the word fail was listed, or go to fail happened twice. The first one happened conditionally, the second one happened unconditionally. And so that allowed you to get to fail without error having an error code in it. And that caused that broke the net. And you look at that and go, who in this millennia is still writing code that looks like that? Who is still using GoTo? And I look at that and go, maybe Dijkstra was right. Maybe there is something seriously deficient with people who write go-tos. I don't know. I don't like to think stuff like that. You know, we should love the coder and hate the code, but you look at this stuff and go, I don't know. That's awful. So the go-to story is an example of a paradigm shift. A paradigm shift happens when there's a change in the way we think. And paradigm shifts in our industry are really difficult, slow, painful things for us to go through. Again, because we don't change minds, we have to wait for people to go away. Because it's hard. In hearing an argument that involves a paradigm shift, we hear all of the words, and we understand individually all of the words, but we don't understand the new paradigm. Because we think we understood all the words, we think we understand what the paradigm is, and so we can easily reject it. But in fact, until you've experienced the new paradigm, you really don't know what you're talking about. So in the go-to debate, there were really smart people who didn't understand really what was being argued about, but they used their intelligence to make really strong, from their perspective, arguments about why they shouldn't have to give up the go-to. which in retrospect were completely wrong. And this is what holds us up. This is why it's so hard to make progress. I remember when the go-to argument was going on, and then one day it kind of stopped, and it got quiet. It's like, are they gone? Let's get rid of the go-to. And we've got rid of it, and we've been fine ever since. So the thing that makes it so difficult is it's hard to understand the difference between a paradigm shift and a bad idea. Sometimes we just can't tell the difference. And sometimes we might think we're doing the radical thing, we're leaping over the paradigm and we're doing the new thing, and it turns out it's XML. And it's like, that was just a bad idea. So the only way to be good at this is to practice, is to try to experience the new thing before making a judgment about whether the new thing is going to be any good or not, and try to not chase fads too much, because very often the fads are chasing the bad thing. So we're going through a paradigm shift right now about functional programming. Functional programming first appears in 1959 with Lisp and is perfected in 1973 or so with the Scheme language, and it is only just now finally reaching the mainstream. It took a long time, but we're finally starting to understand why functional programming is important. And we can look at the timeline here. We started with Lisp and ML and Scheme. Common Lisp recognized what Scheme got right, and so they modified Lisp to include it, but the mainstream didn't get it. Haskell improves on ML, and then JavaScript appears in 1999 with functions as first-class objects with lexical closure, which is also known as Lambda. And it is JavaScript which delivers this powerful idea to the mainstream. And now, many, many years later, we're finally starting to get it, and more of our programming is going functional. And it's important that it do so, because functional programming provides us the tools for dealing better with asynchronous and highly distributed programs. And that's the way we're going. I mean, going all the way back to Fortran, programs have been synchronous things which ran in one process on one machine all by themselves. And that's not how the world works anymore. We've got stuff that's got to run in the cloud, we've got stuff that has to run in the multi-cores, and the old paradigm of sequential programming really didn't get as much leverage there, but functional programming does. And so it's important that we're going through this paradigm shift now. So I'd like to give you one little bit of advice about how to make your programs better. I recommend code reading. Now, code reviews is something that's often done in a project where the very last stage before acceptance is code reading, so we'll get everybody together and we'll read the code and look for bugs. But what happens is that is usually dropped because the project's late and there's not time for it, so we go out without it. Or if we do it, we find bugs and we go, well, that's not very serious, we don't have time to fix it, so we'll just leave it alone. So clearly that doesn't work. What I think we should do instead is do code reading every day. Every day the team should get together and, as a community, read the code that was written yesterday. This idea comes to me from movies. In movie production, they'll hold a meeting every morning where the people in charge of the movie will watch all of the film that was shot the day before. And they're looking to see that it's good enough, look to see what needs to be retaked, and that helps inform what happens in later shoots. I think we should do the same thing in software. One of the benefits is that we can spot places where the code is going wrong much earlier. You know, if it turns out that there's a misunderstanding about what it is we're building, we can catch that every morning. We can all get together and say, no, that's not what we're doing. It also provides for better team building and mentorship, that the senior programmers on the team can be giving guidance every morning to the junior programmers, and very quickly we can level everybody up. So that's the end of my story. And I'd like to leave you with just one piece of advice. And please, I want you to do this. It's really important. Don't make bugs. Thank you.
Tenemos 5 minutos para preguntas.
Sure.
La pregunta que era es si la moda actual del tipado estático es un cambio de paradigma o una mala idea. De que falta tiempo todavía para ver en cuál de las dos categorías cae. Tenemos entonces 5 minutos para hacer preguntas. ¿Ha quedado tan claro? ¿Dónde hay? Ah, vale. Pues ahora te llevan el micrófono.
Hi. Hello. Just a little question.
Can we take the music down? I'm having trouble hearing him.
Great. Thank you. I would like to ask you, what do you think about the GS fatigue? And this is, if you think this is something real or it's just something that some people is just spraying in the social network.
I'm sorry, what do I think of what?
JavaScript fatigue. Just every time appear new frameworks, new ways to code JavaScript, so the people start to say this bit tired to learn every time everything's new. It's called, I know, sorry for my pronunciations, JavaScript fatigue. Que le traduzca alguien, la fatiga del JavaScript. JavaScript stress, JavaScript fatigue. Fernando, échame un cable.
I'm just asking about something that, at least in Spanish, it's called fatiga de JavaScript, JavaScript fatigue. So I'm not sure if it's the same term.
Oh, so I don't know what that is, but if it means we're getting really tired of JavaScript, yeah, I understand that completely. So JavaScript was never intended to be the language that dominates the world in the way that it does. If it had been that language, I'm sure it would be very different. Now, JavaScript is succeeding because it, I think, took a couple of really powerful ideas. It took the Lambda idea from Scheme and coupled it with an idea of dynamic objects. And doing those two things together in the same language was absolutely brilliant. Unfortunately, the language has a lot of other stuff in it which is not. And we deal with that. And in particular, there are a lot of people who imagine themselves to be very clever, who are using all of the stuff that's not good, going, see? And they shouldn't be doing that because it makes your life harder because you then have to maintain their code and it's bad. So I'm hoping that someday we'll get a new language that replaces JavaScript, which keeps the ideas that JavaScript got right and removes everything in it that was wrong and maybe adds one or two additional things to help move us forward in the future. And I think the thing we probably want to add is actors or processes or some way of managing distributed computation, because that's the next important thing that we need to figure out. So I'm hoping that language comes soon, but I haven't seen it yet. I've seen a lot of people working on new languages, and that's great. I encourage all of you to be developing new languages. I'm hoping that one of you is the one who figures out what the new language should be. And that'll be great. And then we'll move on, and we won't need frameworks anymore. We'll just have a language that works.
¿Alguna otra pregunta? Si estás en el fondo, levanta el móvil porque no se os ve muy bien allá en la oscuridad. Los que están en Mordor, ahí no se les ve demasiado. Ah, sí, tenemos uno ahí.
Well, thank you for your talk. I would like to ask, since we don't have to make any bugs, and since there is a lot of people right now that are coding and we need a lot of new code every day very fast, Don't you think that it's necessary that the language is more strict and don't let people do bad things? For example, I mean, that should force the types that you mentioned, that forces the objects to be immutable and these kind of things. What do you think about that?
Certainly want the language to be more strict. Types, I don't think, provide what we need. They just don't. In the case of Java, for example, which is considered a good type system, because it works against what you're trying to do, people have to circumvent the type system. They'll cast, or they'll have normal cases being processed as exceptions, which is another kind of go-to. Really bad stuff. And then there's the problem with classes. So I don't think types are the solution, but being more strict definitely is. That's why if you're writing JavaScript, your code should pass JSLint without exceptions. Yeah, the one guy who clapped is right. So,
thank you.
Hi, thank you for your talk, very entertaining. What's your opinion about stretching JavaScript to write user interfaces, like the JSX thing that React people do?
I don't know what your JSX thing is.
Okay, thank you.
Sorry. I hope it's a really good idea, but I don't know what it is.
I do have one question. What happens if you make a language that is restricted enough to stop stupid people from making terrible mistakes? Aren't you also stopping brilliant people from doing brilliant, creative stuff?
No. So, well, first off, we'll never stop stupid people from making stupid mistakes. They're too clever and they will find a way. No. But you don't need tricks to do brilliant stuff. Developing software which is free of errors and is clear and easy to maintain, what could be more impressive than that? If you want to show off, write some of that. That's the good stuff.
Thank you very much. I'd just like to share one piece of information that maybe not everybody is aware of it, but Mr. Crockford's background is from the film industry. So if you're looking to start a career as a developer and you don't have a computer science background, don't lose hope. He's the living proof that you can become a guru. Para los que no me hayan entendido, el señor Crockford, él estudió cine, no informática. Y aquí lo tenemos como un gurú reconocido en el mundo entero de la programación. Así que si tienes dudas de ¿debería yo dedicarme a esto? Si tienes la más mínima duda de que podrías dedicarte a esto, hazlo. Aquí tenéis una prueba viviente de que se puede y se puede alcanzar.